Good day to you all. Welcome to the fifth lecture of Ship's magnetic compass. In this lecture, we'll learn about Earth's different magnetic forces, which include T force, H force, Z force, and directive force. Let's start. What is Earth's total magnetic force? The strength of the Earth's magnetic field at the surface of the Earth is called Earth's total magnetic force. It is denoted by T. Right? So it is the symbol of this Earth's total magnetic force is Tesla. The magnitude of the Earth's total magnetic field at its surface ranges from 25 to 65 microteslas. If we freely suspend a magnetic needle, it will come to a rest in the lines of force due to this Earth's total magnetic force. The maximum value of the Earth's total magnetic force is maximum at magnetic poles, that means in the southern pole and northern pole. So that's why if we keep a magnetic needle at the southern pole or northern pole, what will happen, that magnetic needle will try to align itself with the magnetic lines of force. Right here you see in the northern pole the magnetic lines of force is entering like that. So that's why if we keep a magnetic needle in the northern pole, near to the northern pole, what will happen, this magnetic needle will try to be vertical with the Earth's surface. So that's why if we go more than 75 degree to 70 degree latitude, it is very difficult to get our magnetic direction. Right, we'll discuss that about this later on in depth, don't worry. Right, and this Earth's total magnetic force, the value of the Earth's total magnetic force is the minimum at the magnetic equator. Right, this Earth's total magnetic force is a vector, and it has got two components. The component which is on the horizontal direction, we call it as horizontal component of Earth's total magnetic force. It is denoted by H. Right, and the component which is on the vertical direction, it is denoted by Z. Right, these components of Earth's total magnetic force will act in different direction. Right, so this H, horizontal component of Earth's total magnetic force, it will act from south to north. It will always act from south to north. Why? Because we have learned previously that the magnetic lines of force always will travel from south to north. In the other word, we can say that the magnetic lines of force will travel from red pole to blue pole. So that's why this H will always act to the south, from H will always acts in a direction from south to north. And the Z, it will act upwards in the southern hemisphere. You see, we have got, if we keep a freely suspended needle, you'll see that that needle will try to align itself with these magnetic lines of force. So that's why it will be the north end of that magnetic needle will be pointing upwards in the southern magnetic hemisphere, and it will be almost parallel in the magnetic equator, and it will act downwards in the northern magnetic hemisphere. Right, in the skin we can see that this a freely suspended needle which is creating a angle of dip, and the magnetic north pole of the freely suspended needle is pointing downwards in the northern hemisphere and upwards in the southern hemisphere, right? In this picture, it is described in more clearly. If we see that magnetic lines of force, which is starting from the southern hemisphere in that way, and it is entering on the northern hemisphere. So if it follows this direction, so if we divide that vector into two component, one will be horizontal component, another will be vertical component. That vertical component will act upwards in the southern hemisphere, and this vertical component will act downwards in the northern hemisphere, right? And horizontal component will always act from south to north, right? We can see that it is acting from south to north, right? Here we have taken one standalone magnetic line of force. Let us see what happens with this magnetic lines of force. In this magnetic line of force, if we see on the southern magnetic pole where the vertical component is maximum, therefore the horizontal component is 0. So, and we have the total Earth's magnetic force is equal to the vertical component of the Earth's magnetic force. So therefore, if we keep a magnetic needle over here, it will be vertical in the southern magnetic hemisphere. Same in the northern magnetic hemisphere, it will be like that, right? So in the northern magnetic hemisphere is also Z is maximum, therefore H is 0, and the Earth's total magnetic force is equal to the Z force. So therefore, if we keep a magnetic needle in the northern magnetic hemisphere, it will be vertical with the Earth, right? Now let's start from southern magnetic hemisphere, and you see that if we start from southern magnetic hemisphere, once we are going through that line, once it comes to that magnetic equator, here we don't have any vertical component, therefore the Earth's total magnetic force is equal to H, right? And here the magnetic needle will try to be align itself horizontally with the Earth's surface, and there will be no angle of dip, right? And again, once it will start from this magnetic equator, it will start bending downwards, and it will create some angle of dip. Hope you understand up to that much, right? Let us see another important concept of Earth's magnetism. We call it directive force. What is directive force? The strength of the horizontal component is termed as directive force. So the H, right? As we know that Earth's magnetism has total magnetic force has got two components, H force and Z force. The H is the directive force, right? The strength of H is directive force. This directive force acts northwards always, right? This directive force causes a compass needle to align in the magnetic meridian, right? So, and directive force is maximum at the magnetic equator and minimum at the magnetic pole. So the larger the DF means is very difficult to deviate the compass needle out of the meridian. So that's why if we keep a compass needle in the magnetic equator, it is very difficult to deviate that compass needle from the magnetic meridian. Whereas if we keep that same magnetic meridian at the magnetic needle at the magnetic pole, it will be very easy to deviate that compass needle from the magnetic meridian. So that's why it is recommended that if you go once you go more closer to the pole, don't use magnetic compass, because it will be very easy to deviate the compass from the magnetic meridian, right? Let us see what is the basic difference from between directive force and Earth's total magnetic force. Directive force causes the compass needle to align itself with the magnetic meridian, whereas this Earth's total magnetic force causes compass needle to align itself with the lines of force, right? I hope these definitions will help you to understand the magnetic compass better. Thank you. See you in the next class.